So we are continuing with the first tutorial of this semester, and this time we are continuing with quiz 2. We have finished the multiple choice and the true false. So let us go to question 2A of quiz 2. Using a simple diagram, derive the relationship between lattice constant and atomic radius for the BCC crystal structure. It's a very simple question. It is fully covered in the lecture slides and in the book. So again, please stop for a moment, solve it on a rough page, and then compare. So rather than doing any calculations, I have shown you the sketch on which everything is there. You have a unit cell. You have a unit cell. So there are atoms on all the four corners and so on also. But because it is BCC, so we are showing only the body centered material and the diagonal which goes from one corner to the other corner through this whole one, right? So you can add one more diagram. You can add a very quick sketch of the normal full BCC and then show this one. But once you show this one, then if I have to find this length, in terms of radius, right, this is one radius, this is two radius, this is one radius. So in terms of the radius of the atom, it is 4r. But otherwise we have to find it. So you know that any side is A. But if I want to draw the triangle, you see, draw a triangle which is this line, and this line, and this height, this triangle, right? So this base of that triangle, for that base, it is A here and A here. So A squared plus A squared under root. So the length of this diagonal is root 2 into A, right? This you have done, but this is now clear. So now to the final triangle, that now this final triangle is there. This side is root 2A, that side is A. So for this side, root 2A whole square plus A square under root. So that will be root 3A. Root 2A whole square will become 2A square plus A square. So 3A square. When you take the under root, it is root 3A. So on this line, the solution is there. That this line in terms of radiuses is 4r. And this line in terms of A is root 3A. So 4r is equal to root 3A. This is the equation between the lattice constant and the atomic radius for a BCC crystal structure. So of course you will write a few lines, but I have explained the whole question to you, right? So relatively simple one. Again, most of the people in the class got it right. But I feel sometimes really bad or whatever that this is something which was explained as a full lecture. The sketches are there in the book and everywhere. So if somebody, does mistakes on this type of a thing, which is very, very basic, BCC, FCC are the only two cubic crystal structures that we are doing. And this is very basic. So if some of you get lower marks than what you should have on such a simple one, then I feel a little sad that it is not that you are not intelligent. It is not that during the lectures we have not covered it very well. It is just that somehow you did not give enough time to it to revise. Let us now move to question 2B of quiz 2, which will be the last question in this tutorial. A tensile stress is applied along the longitudinal axis of a cylindrical brass rod that has a diameter of 10 millimeter. Determine the magnitude of the load required to produce a change in diameter of 2.5 into 10 raised to minus 3 millimeter if the deformation is entirely elastic. Values of elastic modulus and Poisson's ratio for brass are 97 gigapascal and 0.34 respectively. The drawing is given, right? So this is a cylinder, right? Originally it was this dashed line. Later on, when it was pulled, it became the solid line. The force is F. The initial dia is Di. The final dia is Do. The initial length is L0. The final length is Li. The values are all given here. So once again, as I said, please pause my video, solve it on a separate page. And I keep on reminding that not just in my course, in any course, if there is a numerical problem, first read it carefully, give it 1 extra minute, then write the knowns and the unknowns, and then start solving it. Then it will be a very good thing. So if you are going to my next slide, then you have already solved it on your rough page very, very carefully. So let us see. I am just recapping that this is the diagram. There is a tensile load, elongation is happening plus reduction in the diameter. So the change in diameter is given as 2.5 into 10 raised to minus 3 millimeter. It is given, right? When the length increases, the dia decreases. So this delta D is a minus, right? Okay. Now, very simple, that a strain is change upon change, right? Change in length upon length. So if the dia is changing, dia is a length. It is millimeter. So a strain is change in length upon length, delta D upon D naught. So delta D is given, D naught is given, and this minus sign is very important. So in this direction, if you call it the X direction, then the strain is there and it is minus, which means that the dia was decreasing. Next step, the strain in the other direction. This was in the diameter direction, So now in the length direction, So you know that Poisson's ratio is the ratio of axial to transverse. So therefore, if you want to find the epsilon z, then it is minus epsilon x upon nu, right? So epsilon x you have already found, and nu value is given in the problem. But remember, there is a minus sign already in the equation, and then there is a minus sign in this value, so this will become a plus number. And because it is a strain, so there is no unit. If you had not put a minus there, you will get a minus strain here, which will not be right, because the diametric strain, diameter was decreasing, so the strain was negative. Longitudinal or axial, the length is increasing, so the strain is positive. Next, you know that in the elastic region, this was a very simple problem because we said that everything is in the elastic region. So in the elastic region, sigma is equal to E epsilon, and the values are given. So epsilon z you have just found out, and E value of this material is given. So this is sigma, right? Remember if you are writing 71.3 into 10 raised to 6, then it is only Pascal. If you are writing just like this, megapascal, so this is megapascal. So remember that always be very consistent with your units, Otherwise, in strains we were not worried, because this is also millimeter, this is also millimeter, right? This is also millimeter. So in a strain we were not worried about, but now you know that this is sigma in. So this is the sigma in the length direction. Then we know that stress is force upon area. So force is stress into area, and this will be because stress is force upon original area, right? So original area is pi by 4 d square, or whatever way you want to write it. So now force, how much force is required? A stress you have found out, so write the stress, write the 10 raised to 6 for the mega, right? D naught is given already, so write the D naught, but now in meters. Remember, not in millimeters. D naught was 10 millimeters, so 10 into 10 raised to minus 3, this 2 is already there, and this comes out to be 5,600 Newton roughly, or you could write 5.6 kilonewton, right? You could write 5.6 kilonewton. So again, a very simple, because it was only elastic. If it had gone to the plastic region, then you need to know the diagram, and then you need to draw some lines and so forth. But in the elastic region, sigma is equal to E epsilon. So it was a relatively simple question. The only thing is that the change in diameter is given rather than the change in length. So you find the strain in the diameter side, and then you find the strain in the length side, and then it is a very simple problem.
Let me just leave you with a small, more enjoyable moment. A man was in his office and he got too tired and so on with meetings and work and so on. So he said that for a couple of minutes, I will relax. So he made a call and said, "Hello, darling, how are you?" And then he got the answer, "What? You are in such a good mood? You are calling me darling? And what happened to the fight in the morning when you left for office?" He suddenly closed the phone and said, "My goodness, I called my wife." Joke is over. So that is it.
So in the end, just exam strategy and further practice. You know that we have only covered chapters 1, 3 and 6 for your midterm. So the first thing, solve all solved examples again independently without looking into the solution, without taking anybody's help, right? In the lectures and in the book, all solved examples of chapter 1 and 3 and 6, do them again as a practice independently. Next, solve all homework problems independently, right? I am always right that we smile about it and so on, which actually we should be a little sad about it, that some of the people, if they just copy the homework and submit. But now, whether you did it yourself earlier or whether your friend helped you, now once again, all the homeworks which are covering chapters 1, 3 and 6, solve all of them independently without anybody's help. Then you will become really strong. If you do this, if you do all the solved examples and all the homework problems independently without anybody's help, then I can guarantee you that you are above average in the class. If you want to be top of the class, A minus A and so on, then solve some selected more difficult end of the chapter problems. At the end of every chapter, chapter 3, chapter 6, there are numerical problems given there. So either, it's your choice, you can solve all of them. Some of them are already in the homework and so on. You can solve all of them, okay, great. But if you want to save time, then just read through the problems at the end of chapter 3 and chapter 6 and see which ones are more difficult for you. So just solve a few very difficult ones which were not there in the homework. Now you are sure that I have done all the examples again, I have done all the homework problems again, and I have solved a few very tough problems also. So now I am A material. With that, this is the end of this tutorial. All the best for your midterm exam. But I am wishing you, I am praying for you, but this also needs a little bit of revision and hard work from your side. Thank you. Ma'as salama.